Dying ReLU problem. Let us understand what is dying ReLU problem that is faced by ReLU activation function. Okay, we already learned about ReLU activation function in the last lecture. We saw that this is a very commonly used and a very popular activation function because of the advantages that this provides. But at the same time, it has a slight disadvantage, that is, it faces dying ReLU problem. Let us understand what is this problem, how it is occurring, and what can we do in order to rectify this. Okay. First of all, the issue here is that whenever a particular neuron hits the dying ReLU scenario, after this point, irrespective of the input that you may provide, this neuron will always output 0. This is the problem called dying ReLU problem. The most important point here is, irrespective of the input you may provide to the neuron, it will always output 0 as its final output. This is the problem. So you understood at this point that once the situation is hit, there is no way to come back. It is permanently in this scenario. Okay, so neuron will effectively stop learning and it is as good as being dead. That is why you are calling it as dying ReLU problem. Okay, let us see how this is getting hit and what exactly is the scenario. We'll start from the ReLU activation function. We already learned about ReLU in the last lecture. We understood that f of x, whenever x is given to ReLU, it will output x whenever, that is if x is greater than 0. What if x is lesser than 0? Whenever x is lesser than or equal to 0, it will output 0. This is your ReLU activation function. At this point, you already know that whenever x is negative, output is 0. And what I told you just now is that irrespective of the input, ReLU is going to output 0. That means you can somewhat understand that there is some particular factor which is making the input always negative. This is only how you can hit dying ReLU problem. What is the reason? Because you know for positive input, ReLU will give you some output. I am saying you, irrespective of the input, ReLU is giving you 0 only. That means there is some factor which is making the input negative irrespective of whatever you are giving it. Okay. So let us understand how this is happening. For this, we'll take one neuron as example. Let us say this is one neuron somewhere in your neural network. Then there will be some weight and some bias which are associated with this neuron. Whenever you give any input, let us say x is the input, what happens is initially this will be multiplied with the weight and bias will be added to it. Then that neuron output will look like, that is, before giving to activation function, you will do, let us say, z is equal to wx plus b. So what is w here? W is the weight of that neuron and b is the bias in that neuron. So this is the weighted output that is coming out of the neuron. This weighted output is what you will give to the activation function. So when you give this weighted output to activation function, then f of z, this I am telling you is always 0. This is what I am claiming. As of now, assume you have hit this scenario. That means your f of z, the activation function output, is always 0. If this has to be 0 always, then this weighted output of neuron should be negative in all cases. Then only you can hit 0 with the activation function. Next thing you have to understand is, how is it reaching a scenario where your weighted output is always negative? So once it is negative, the remaining part is clear. But the first question is, how is it hitting this negative scenario? So how it happens is, let us say you are training some particular neural network. There are a lot of neurons here, many layers here. You are training this. If you are doing some sort of, let us say, aggressive learning, this is just one example, okay? One example scenario. Let us say you made some particular wrong weight update. Due to this wrong weight update, what happened is your weight in one particular neuron, let us say this became -1. And maybe bias of that neuron became -10. If this is the scenario, let us say you give x is equal to 0. then your z is equal to wx plus v. Your z is equal to w into 0 plus minus 10, which will give you minus 10. This is a negative output. Even if you give a positive output, let us say instead of 0, you gave x equal to 3. Still it will be minus 1 into 3 plus minus 10, which will be minus 7, which is still a negative input. So like this, when your weights and bias gets manipulated wrongly because of some wrong updates on weights and bias, you may hit a scenario where whatever input you may give. So when I say whatever, now you can ask me, okay, if I give, instead of this, if I give 30, then this will recover. But the point is, your inputs may be coming in some particular range. Let us say you are training for some purpose. So whatever be the purpose, generally there will be some particular range in which your inputs are coming. So your neuron may get some updates, some particular updates, because of which whatever input among this range you may give to it, it will always stay negative. This is the scenario of dying ReLU. Whenever it hits this scenario, after this point, this output Z, that is the weighted output that is coming from the neuron, that will be forever negative. When this is forever negative, the output of your ReLU, that will always be 0. Next question is, why am I saying it will always be 0? If weight got updated this way, that is, if I am saying that because of wrong weight update, it became negative here, and wrong bias update, it became negative 10 here. If this can happen, then because of some other update, it can recover as well. That should logically be the case. That is, if it becomes 0, becomes minus 10 because of some update, it may also become plus 10 because of some other update later. So you may think then there is a situation where you may come back and then this dying ReLU problem is solved. But it is not. Let us see how it can never get solved, and once it falls to this scenario, it will forever stay there. So let us understand how that is happening. Okay. For this, we need to understand how weights are getting updated and why that update won't happen after hitting the dying ReLU scenario. Okay. First, we'll understand how updates are happening. Okay. Let us say this is your neural network. During back propagation, you are going to take the gradient, and gradient will be back propagated. This we discussed in previous lectures also. When you take this gradient backward, if the gradient itself is 0, then what is going backward is 0, which means no update. In this scenario, if you take, this is your f, that is f of z. Then if you differentiate this, del f by del z, for ReLU activation function, we already discussed derivative in the last lecture. For ReLU activation function, this will be 1 whenever z is greater than 0. This is the scenario. But this del f by del z, this will be 0 whenever z is less than or equal to 0. And this is the problem here. Once you hit the dying ReLU scenario, I told you that z will be lesser than 0 at that point. Because z is lesser than 0, your derivative will be 0. When your derivative is 0, then what happens? You know, at this point, output is also 0. Output is also 0. Derivative is also 0. Next thing you have to understand is how derivative is used for updating weights. So we have not reached till updation of weights, but I'll just give you the formula and give you a basic idea of how weights are updated. Later when we learn gradient descent or something, we'll go into detail. Okay, for now understand that when you want to update weight, it works like this. Let us say your weight is W. Then your updated weight W dash, that will be the existing weight W minus eta, which is a learning factor, this into del L by del W. So this is how you will generally calculate how to update your weights. W is your existing weight. In order to update that, first you will see what is the loss, that is at the final output of the neural network, what is the total loss. Then when you differentiate that loss with respect to this particular weight, you will understand what is the contribution of this particular weight W towards this loss L. Whatever be the contribution of this weight W towards the loss L, that should be the factor by which you should modify W. So that is how you are getting the factor here. Next thing you have to see here is this del L by del W. How are you going to calculate that? You will calculate it something like this. Let us say del L by del F. Then you will say del F by del Z into del Z by del W. This will be how you will be actually calculating. But here, this term del F by del Z, this will be 0. You understood this, right? Because this will be 0, this whole term will become 0. That means derivative of loss with respect to this particular weight will become 0. That means this term will become 0, and then your W dash will be equal to W. Whatever be your existing weight, that will be your new weight up after updation. That is, there is no updation done to the weight at all. So once you hit this dying ReLU scenario, weights won't be updated. Whatever be the weight, it will stay as it is. Whatever be your bias, it will stay as it is. There will be no further updation to it. Because of that, forever it will stay as a dead neuron. It will be in a dying ReLU scenario. It will be a dead neuron forever. Okay, this is the scenario. So you can understand this like a loop. That is, initially you had 0 as the output. This is the starting point. When you had 0 as the output, what happened? Your gradient also became 0. 0 became your gradient. When your gradient is 0, then what happens? Your weight update did not happen. When your weight update did not happen, then what happened? Again, your output will remain 0. So this is like a loop. It will always remain as 0. There will be no updates on weights, and it will always stay in this dying ReLU scenario. Now let us see, how are you reaching this scenario at first? I gave you one example. What are the different reasons because of which you can hit the dying ReLU scenario? One reason we already discussed. Let us start from there only. That is, if you make a wrong weight update. Let us say you kept this learning rate eta. If you kept that eta very high, then what happens? If your learning rate, if this is very high, then your weight update may be a large update. Because of this aggressive update or a large update, what happens? Your existing weight W dash, that will be wrongly modified. If it so happens that this is wrongly modified in the negative side, then it will be a larger negative value, and after this point it hits dying ReLU scenario and there is no coming back. Okay, so the same way weights are updated, bias will also be updated. Bias can also get the same wrong update. This is one scenario when you do aggressive updates using large learning rate. Okay, aggressive update using large learning rate. This is the first scenario. Second scenario is, what if before starting the training you made wrong initialization of data? Your initialization that you did is wrong. If your initialization is wrong, what happens is, initially you have to pick one particular value for weight and one particular value for bias. This is how your learning starts. Before your learning starts, you have to say maybe my weight is equal to 0.001 and my bias is equal to 0.01. Something like this. If it so happens that you make a wrong weight and bias initialization, then maybe after few steps of learning, it will reach into dying ReLU scenario. This is the next thing. And from the previous example, you already understood that if your bias is largely negative, then this scenario is guaranteed, because whatever you may do with the weight, your bias will always take it towards the negative side. Okay, so these are the major situations where it will reach a dying ReLU scenario. And one thing you have to understand here is, once it reaches this scenario, then I already told you, you can't come back. But what are the problems it is going to cause? First thing is, you have a neural network. Why are you having this neural network? Why do you have a lot of layers and a lot of neurons? The reason is, you want to model complex functions. This is your whole point. That is why you are having very large neural network, a lot of layers, and you're using activation function because you want non-linearity, you want multiple layers of non-linearity, and it should model complex functions. The problem here is, if a lot of your neurons hit the dying ReLU scenario, let us say this is gone, this is gone, this is gone, this is gone, like this. If lot of your neurons hit the dying ReLU scenario, even though you are having a lot of neurons, effectively you are only having very less number of neurons now because all other neurons are dead. You may think you designed a very large neural network, you have a lot of neurons, but because it hit the dying ReLU scenario, even though you have this much of a large number of neurons, still most of them are dead by now. So you effectively have a very small neural network with very small count of neurons. So this is a bigger problem that is caused by ReLU. Your network capacity will be reduced. Just think like this. Let us say you have millions of neurons and you designed a very large neural network, and then because of dying ReLU, if 50% of your neurons are dead, all your neural network is wasted, right? This is the scenario. In order to add to this, the problem is, even if a neuron is dead and it is giving you zero outputs forever, still it will use your computation. See, you are having a neural network, you are using some computation power, let us say, and you are having memory. All these will still be consumed by this neuron. Why is it? Because neuron has to do the calculation. It has to calculate Z, then it has to pass it through the activation function. Then only it will understand that output is 0. So even if it is dead, it is effectively dead. It is always outputting 0. It is not like not having a neuron at all. Instead, it will consume your memory and CPU. So your memory and computation power both are used up by your neuron, even though it is effectively dead and always outputting 0. So this is actually adding more issues to your problem. You are having less number of neurons now because of the dying ReLU problem. Over and above that, these useless neurons, they are going to consume your memory and computation power. So this is an even bigger problem with dying ReLU. And before we end this lecture, let us have a short look at what can you do to prevent this. You know ReLU is very widely used, so you will also be using ReLU in a lot of applications. So you should know, how can you avoid this dying ReLU problem? If you avoid this, then ReLU is even better. Okay. One thing from what we already understood about how it is hitting that scenario, you know that you have to take care of initialization. This is one important part. Initialization of weight and bias. Whenever you are doing, you have to make sure that those are good enough such that dying ReLU won't be hit. Second thing is, so when I say good enough, what you would ideally do is, you would give very small values for your weight and bias, and then slowly, according to the scenario, you will increase it by small extents. Okay. So when you are initially putting, always make sure that you are putting very small values which can't actually affect your network. Okay. This is one scenario. Next thing is, you can think of normalization, maybe one. Okay, we haven't reached normalization yet. Still, I'll just give a basic idea. Okay, normalization, you can see this as a way of taking all your inputs or outputs to a single scale. So on every particular layer, if you apply normalization, then all these outputs will come into one particular scale. So this will avoid exploding kind of outputs. So your updates will also be under your control. So it will be kind of bounded. That is what you do with normalization. When we reach normalization, we'll go into detail of that. Another option can be maybe something like gradient clipping or something, with which again, these are ways of avoiding exploding gradients. That is what you're going to do with normalization or with gradient clipping. What you want to do is, you don't want your gradient to explode. If it explodes, then your updates will be a problem. I already told you here, we saw that updation is done using the gradient, right? We used del L by del W. Using this gradient, you did update. So if your gradient explodes, if it becomes a larger value, your update will automatically be larger. Your W will be changed by a big extent. That can always affect your W. If it gets changed to a big extent on the negative side, then your complete learning can go for a toss. Okay. One practical way of resolving this is using something other than ReLU. So I already told you that ReLU is very important. ReLU has a lot of specialities. So you can't let ReLU go away. Instead, there are certain activation functions which are slight modifications on the ReLU. So something like there is something called as leaky ReLU, or there is something called ELU. These sort of things, these are modifications over ReLU which will help you avoid this dying ReLU scenario. Okay, so this is how you are going to avoid dying ReLU problem. Understand that what is dying ReLU problem, that is what we discussed here. We understood how it is hitting, why is it never able to recover back once it is hit, and what you should do in order to avoid this problem.